Here in our universe as we know it, once an outcome has occurred, there's no going back. Once you open a bag of potato chips, you can never return that bag to its unopened state. The air molecules from inside and outside have already mixed with one another, even if you reseal it. Once you cut down a tree, you can never return the tree to the state it was in prior to you cutting it down, even on a quantum level. Once you measure a particle's spin, you can never return it to its pre-measurement state. We have only the one universe that we inhabit. And while future events do not yet have determinate outcomes, past events all do. But what if there were copies of our universe out there, far beyond the limits of what's observable or measurable, that were identical to our own? If the universe is infinite, and string theory suggests that strings can only vibrate in a finite number of ways to form particles, is it possible that a version of me could exist somewhere else in the universe? If another version of yourself were to exist in a region of the universe with different physical constants, such as a significantly altered gravitational constant, how might such variations affect my physical appearance or biological structure? These are two very big ideas and concepts, and certainly worth investigating. In order to answer them, we're first going to have to unpack what an infinite universe, string theory, different versions of ourselves, and different fundamental constants all have to do with one another. First, there's the quantum multiverse. It comes from the notion that every time two particles interact with one another, there isn't a definitive outcome that absolutely must occur, but rather an array of possibilities that could occur. Sometimes these possibilities are discrete. An electron can be spin up or spin down when you measure it, and as long as its spin remains unmeasured, it can exist as a combination of both states at once. Other times, the possibilities are continuous. An electron and positron, when they interact, will annihilate into two photons, each with 511 keV of energy. But those two photons, although they'll always travel in opposite directions from one another in order to conserve linear momentum, have no restriction on the orientation of each individual photon. They could travel in the X direction, the Y direction, the Z direction, or any combination of the three. Each time a quantum interaction occurs, there isn't a definitive outcome that we can predict. We can only predict the spectrum of possible outcomes, weighted by probability. It's only when we make that critical measurement that we can determine which outcome actually occurred within our observable universe. In quantum mechanics, we typically describe this behavior probabilistically through a wave equation. Instead of particles having definite properties like position that can be known at every step along the way, what we're used to from a classical deterministic view of reality, we instead can recognize that particles exist in what we call a superposition of states, where each possibility for its value is weighted by the probability of it having that value at that moment. These entities propagate like waves, where they do not take on a definitive value while they're non-interacting. However, when we do make a measurement or force an interaction, we then instantly determine that value, and only one such possibility is realized by that measurement or interaction. Those outcomes might well all occur just in other universes from our own. Mathematically, those universes fit into a mathematical structure known as a Hilbert space. But if we want to consider a quantum multiverse, we might imagine that somewhere far beyond our own observable universe's boundaries, what we might call those other parallel universes do indeed exist, where all of the other possible outcomes have occurred as well. That quantum multiverse is one notion of what a multiverse can be, but there is another, and that comes to us from the world of inflationary cosmology. According to the theory of cosmic inflation, prior to the Big Bang, space wasn't filled with particles of matter and radiation, but was rather empty, save for energy that was inherent to space itself, field energy that was inextricable from the very fabric of space. Under those conditions, space expanded at what we call an exponential rate, where after a certain brief amount of time, all three dimensions double in extent, and then when that same amount of time elapses again, the scale of space has doubled yet again, and so on and so on. This can take even a minuscule region of space initially and inflate it to gargantuan proportions. When inflation ends in a specific region of space, that energy that was inherent to space gets converted into matter and radiation, and that signals the onset of a hot Big Bang. The theory of cosmic inflation thus provides us with an inflationary multiverse, or a second type of multiverse. Although the quantum multiverse had been around in some form or another since 1957 and was greatly popularized in the 1970s, it was only with the notion of cosmic inflation that these so-called parallel universes finally had a potential place to live. While it's untrue that the inflationary multiverse is large enough to hold all of the possible outcomes of the quantum multiverse, it is in fact not. In general, there still remains the possibility that either inflation went on for an infinite amount of time to the past, or the universe, including the part that underwent inflation, was born infinite, which would indeed give all possible quantum outcomes a potential place to reside. The quantum multiverse is the notion that there are different versions of ourselves, or our reality, and the inflationary multiverse represents how large the total volume of all types of space combined are, and whether it's large enough to contain all of those different possibilities. If we assume that the inflationary multiverse is indeed infinite in size, then the quantum multiverse being real is indeed a possibility. And we can consider that perhaps there really are not only copies of us within the multiverse, but an infinite number of such copies. What does any of this, though, have to do with string theory? Within our observable universe, we see that the fundamental constants are the same everywhere we look, as well as at all moments throughout our cosmic history. The fundamental parameters of our universe do not change. Although we do not understand what determines those parameters, they may as well be God-given for all we know. They are not determined by any sort of known physics or dynamics that occurs. These constants that underpin our reality simply have the values that they have, and there's no other possibility for what they could be. Nor is there any reason to expect they would be different outside of the observable universe, whether in other pockets of the multiverse or in any other scenario you can imagine. But if you bring in ideas from string theory, marrying string theory with cosmic inflation, those constants could indeed be different in other pockets of the multiverse. The reason why is not generally appreciated. In the theory of inflation, there's an energy scale at which inflation occurs. And then when inflation ends, that energy gets converted into matter and radiation in the form of particles and antiparticles, into the known particles of the standard model. When we examine the fluctuations in the cosmic microwave background, they provide constraints as far as how hot the universe got during the earlier stages of the hot Big Bang. With data from WMAP, the Planck satellite, and several other projects, we now know that energy scale is somewhere below around 10^16 GeV, or less than 1,000th of the energy needed to reach the Planck scale. The Planck scale is the important comparison point here, because that is not only the energy scale at which our currently known laws of physics break down, and where a theory of quantum gravity would be needed to make sense of physics, but that's supposedly where the string scale comes into play. If inflation occurs at an energy scale that's well below the Planck scale, then there's no reason to believe that inflation has the ability to determine or change the fundamental constants, plunk one baby universe into a different value for any of the string vacua than any other baby universe, or explore different aspects of the string landscape. Based on what we can observe, we have no compelling reason to be certain that inflation has the ability to touch the values of the fundamental constants at all. It is simply an unsupported assumption about reality, much like most of string theory. However, it's important to recognize what string theory is. A tremendously rich theory with a much more complex set of relationships between particles, fields, interactions, and anything else you can imagine than the universe we know, love, and inhabit. String theory is at least a 10-dimensional theory rather than the 4-dimensional universe we inhabit. String theory has hundreds of additional degrees of freedom which correspond to potential interactions, particles and fields that go way beyond what exists in our universe. Most of what is possible is not reflected in our reality. And this brings us to the grand symbiosis of science and philosophy. The realms of physics, quantum mechanics, and cosmology provide us with the tools and theories to explore the how and when of our existence. Yet they leave us pondering the why. Why does our universe exist in this delicate balance? Why are we here to observe it? And yet, if the inflationary multiverse is truly infinite, either in spatial extent or in duration, then there must be copies of our entire universe somewhere within it, including copies of ourselves that are identical to how we are now. If string theory and the idea of the string landscape being fully populated within the inflationary multiverse is indeed correct, then we could have nearly identical versions of ourselves out there as well. However, while the inflationary multiverse gives us ever-growing places to hold all of these possibilities, places that grow at an exponential rate, the number of possible outcomes for a matter and radiation-filled universe grows even more quickly, in a combinatoric fashion. These discrete and continuous possibilities for each quantum process result in a greater increase in what's possible than the rate at which inflation generates more and more potential space for those possibilities to exist. As time goes on, the fraction of universes that admit a copy of our current observable universe gets smaller and smaller, always asymptoting towards zero. While parallel universes are a fun thought experiment and a playful arena for theoretical physicists to explore ideas, there is no evidence at all that this idea has any tie to the reality that we inhabit. While theory allows us to imagine worlds and universes that might be, it's vital to keep in mind that most of them, and perhaps even all of them, are worlds and universes that never were. This reflection brings us to a poignant realization, the uniqueness of our universe and our place within it.